continue. And I know it's most of the information, at least the algorithms, again, are familiar to most of you, right? Some of you have forgotten them. But again, the key to remember is that these, you can emulate many problems, not only, you know, visual shortest path problems with this approach, right? The goal could be, I don't know, retirement, finishing college, getting a good job, and so on and so on. You're making decisions, right, at each step, right? Anywhere you're making decisions, right, these approaches will apply. So I got out our good old friend visualizer, and if you have a maze, right, let's clear the board. I think I know clear path, right? So it's a maze, right? So the depth first search is a horrible idea here. Why? Because we are gonna just find the first solution, right? We got a solution, and this can show you why it's not such a good thing here, right? So again, we look at some other approaches, right? So depth first, but there's a big advantage to depth first search, right? You sort of keep going, right? You don't really, if you ignore where you've been, right? You just keep going until you find something. There might be some problems where depth first search is like the only real solution, because you don't really have such a big search space. You just want to keep going until you find something, right? So you don't have a very, there's mention of, the book mentions frontier size. So this means that at each step you don't really have a, you're expanding only, you have only a relatively smaller set of choices you're making, right? You keep going deeper, right? And you're only looking at that particular node where you are, right? In the breadth first, you're expanding, right? Let's compare this, right? Again, so DFS, right? It's only one choice, but you're making only a few choices, you know, you keep going basically, right? But you end up with a huge, really bad solution, right? But again, you didn't have to spend much memory, right? So you keep going. pretty bad, right? Right, but it's a solution, right? So compare, well, I don't want, okay, stop. I'll do it again, but I want to do the breadth first, right? Okay, come on. Can I then change speed to this? I forget now. Oh, speed fast, super fast. No, it's a fast speed. Just JavaScript is, I guess, kind of a bit slow here. All right. Let's do one more. Let's do BFS, right? So what's going to happen? Guarantees, right? So the cost is your frontier, right? As the book says, right? It's expanding, right? But it'll find the solution, the best solution, right? In this case, not a bad choice. But again, so these are a bit of BFS, DFS, right? But we have a lot of options how to improve, right, on these two basic things, right? So we could do a depth limited, right? Iterative deepening. So this means it's like depth first. You keep depth first, but you say don't go too deep, right? If you go like 10 levels too deep, right, you stop, right? So it's possible we don't reach solution with this approach at all. We just don't find it, right? But we sort of like, it's going to be efficient, right? So, right, we might need to eliminate some cycles, right? So, iterative deepening search, right? So, if we don't find with the depth 1, we go with depth 2, depth 3, and so on, and so on, and so on, right? So, it is kind of like low memory usage, because we're using depth first, but also eventually we'll find it if it exists, right? Because we sort of keep going larger and larger frontier, right? We check 1 level deep, 2 levels deep, 3 levels deep, right? And eventually let's check 60 levels deep. Let's see if we have it here. Do we have it? We don't have it here, right? We have our good old friend A star, right? Do we have A star here, right? Right, so this is iterative deepening. Check depth 0, check limit 1, right? Check 2, right? Check 4, right? So keep getting, so you can of course combine them in different hybrid approaches, right? So one approach is you have a huge search space is start from the end and start from the start, right? Bidirectional, right? from both directions. So let's do that. Bidirectional swarm, right? Let's try that one. Right? And when we meet, right? But technically, it does not guarantee the shortest path. You just keep trying to find a solution. So both the end goal and the starting positions, you start off like try to meet in the middle somewhere, right? That's where we did, right? Swarm, greedy best first search. Let's see what happens with greedy best first search, right? So greedy approach. You guys remember from my greed is usually not gonna work, right? Greed is easy to implement, right? Cheap, but maybe you have a comment on greed.
No, the thing I wanted to, I'm not pointing at this one, but like, this course has taken algorithm and analysis and so on, but
Yeah.
we haven't for some weird reason.
You have not?
We haven't.
Wait, you have not taken analysis?
No, it's scheduled for the next semester.
Oh my god, so it's actually not fair to you guys.
And it's also, kind of feels like, should it also be from like logical course content perspective?
Yeah, but the thing is, okay, so wait, okay, I'm not telling, because I was just teaching algorithms last semester.
Yeah,
This is these guys. So you guys are smarter than your, right? Yes, and you guys are so. So the question is, when are you going to take algorithms?
next semester, optionally.
Optionally, but that's year 4 for you, right?
And actually, we have also taken the programming languages, which was like algorithms are prerequisites for programming languages.
Yes.
So,
So wait, I'm telling you, how is it possible you didn't take algorithms?
I don't know.
I don't know. Interesting. So I guess So you see, I was coming here. For some reason I thought you guys took algorithms, right?
We had data structures.
Yes. Okay. So the guys in the back, right? Yes. Sort of like you're omniscient, right? Like you know things, right? So, but I guess what this means is, right? Well, the book explains again. So we'll talk more about the search algorithms, right? This is like I said, you won't have to like do them from scratch in this course, right? Because that's more part of the algorithms course, right? But at least you will see some of the approaches. Okay, so that's why I was kind of skipping them a little bit, right? But so Dijkstra, how it works, so breadth first, depth first kind of makes sense, right? Even if you have not, right? The other ones are just, sort of like improvements, right? So informed, right? So informed search strategies if you know something about what you're doing, basically, right? So the key feature is you have some cheat code. You need the cheat code. So the cheat code, of course, for these is a distance function, right? You have the coordinates. You can estimate. So let's see about this approach. Let me clear everything, right? So here, right? I like short. So A star, right? My friend A star, which is great in games, right? Anywhere you have 2-dimensional, 3-dimensional space, right? What's going to happen? Guys in the back know what's going to happen is going to be
A star.
yeah, straight line, right? So how about here? Well, let's do the clear path. No problem, right? So why does this work? Because you have a cheat code, which sort of you have a heuristic, you have a rule, right? So it's domain specific, right? So generally, what kind of rule do you want? You want sort of like a rule for easier problem. So in this case, the easier problem is exactly the same as the actual problem because you have the rule. Of course, we're not allowing diagonal moves in this particular version, right? So let me clear it, but let's see what happens. Make things more interesting, right? I'm going to move this around a little bit. Let's say here, right? But what I'll do is I'll add a big val here, right? So will this rule still work? but it doesn't work. I think shift maybe. It's been. Oh, come on. Okay. Come on, it didn't work. All right, all right. So A star is sort of cheat code, but it'll hit the wall, right? And then it will keep sort of like go into, well, it will keep trying the moves, which sort of like, you know, legal moves, right? Not hitting the wall, which are closest to this. So let's see what happens, right? You see? Right, so what happened is this, right? None of these moves directly led to the solution, right? So I start exploring moves outside. So this is the cheat code is sort of like an extra function. So again, those who have taken Dijkstra, right? It's basically Dijkstra with the extra cost, extra function. That's basically all it is, right? So as soon as you got here, you have straight sailing, right? You go back. Does this make sense?
Well, it makes sense because what we know when we're like where the target is located.
Yeah. So if you know, again, but if you have like this very general problem, right? Like, I don't know, you know, getting a good job, right? Right? You don't have a good, well, your heuristic function, you don't really know how to, you know, you could come up with some function, right? But you don't really have a function, you know, until you reach the goal, right? So it's not gonna, you know, it's an unsolvable problem, right? So, and again, if I do something, you know, I make more things more evil, right? I'll make more things more evil. Come on. So let's see what happens now. So you can probably imagine what's going to happen is it will explore things here, because again, I'm calling it, right, agent, right? Because there's no knowledge, there's a wall, right? It's just that the algorithm does not know about the wall, right, itself directly. It just explores possible moves, right? And, you know, until it hits it, right? So, let's do this, right? So, in this particular case, it got to here. What's interesting, actually, it got here, it kept exploring different positions, right? This is also a possibility, right? But this is slightly shorter, right? So here, right? So it explored also towards the alternative. However, if I did this for Dijkstra, right? What would happen, right? This would be much longer process. Look at this, right? Same solution, right? But optimal solution, shortest solution in this case, right? But just took much longer, right? So A star is great if you have a cheat code. And cheat code is generally a solution to an easier problem, right? If you can figure out an easier solution, right? I mean, problem if there's no walls, right? And this is a good one. So can we come up with something really evil to make the A star sort of break? Well, if you make walls all around, just leave a little tiny hole. Let's do that, right? Let's make this, you know, I like to break things, right? So let's see what happens. I can't. Oh, it sort of works, right? I don't know. Come on. I don't know what's happening. This yeah, I'll just do this. Yeah. Oh, if I hit, okay. So there's only one way, right, out of here. Well, now, let's see what happens. Okay. Oh, here. Okay. Let's see what happens now. We're evil, right? Right. Immediately, right? You see, once it got out, it basically had the cheat code, led it to the best solution, right? So, but of course it had to, first it tried everything inside the box because it had no knowledge that there's a wall, basically, right? But still, again, this is a really, A star is a great algorithm, right? So, as long as you have the solution, as long as you have cheat code, right? So greedy first, right? But greedy first here, of course, like I said, if you don't have a greed, right? Greed, you just hit the wall, right? So A star, right? You have cost, and you have this evaluation function. It's probably most widely, well, it says one of the most widely searched algorithms in AI, route finding, robotics, right? And there's some improvements to it as well, right? So, yeah, for find of characters, you know, right? So, search contours, right? So, yeah, contours, right? Now, there's for A star, again, this is something we covered in algorithms class. Sometimes you want to, in A star, right, you're not allowed to overestimate the cost. So that's one limitation of A star. Your cheat code should give you the best case scenario. Your cheat code cannot give you the cost which is over the optimal solution. Why? Basically shows up that if you have an overestimate, you might not get the optimal solution, basically, right? So in this case, it's completely easy because you have a Euclidean search, a distance function, just simple distance function, and obviously that is going to be the best case scenario, right? In a two-dimensional space, works for three-dimensional spaces, right? Now, problem with A star in general, right, of course, is how do we reduce memory usage, right? Because as we saw here, right, we need to store the data about where we've been, right, all the search conditions, right? So sometimes if it's a huge space, right, we might want to eliminate, maybe you don't need to check everything where you've been, maybe you can just only check where you are currently around, basically, right? So sometimes you can eliminate some states, from the memory completely, right? So there's some improvements, like something called like beam search, right? You only check in each, let's say like here, right? Beam search, right? You only, let's say beams, okay, so this is, let's say 5, right? And you can say beam size is 3, so you only check 3. Let's say beam 3, right? You only check 3 best, right? You don't check the other ones, right? Obviously, you need a good algorithm to say, okay, which ones are the 3 best choices, right? So again, if you have some way of eval, right? Here would be crucial, because otherwise maybe these are completely good choices, lead to a good goal, right? So beam search. Deepening, right? So bidirectional. So you can have, if you have rules, maybe you go both ways, but you also have some sort of a cheat code which leads you to say, okay, which way to go, right? From both. So let's see, do we have bidirectional here? I think we do. Yeah, we do. What's going to happen? So it's probably going to explore both sides. This will take a while, right? You see? Two swarms meeting. Okay, does not guarantee, but I think in this particular case, let's see, one down, it's exactly the same cost as A star on a Dijkstra. It's just that in this case, there's multiple solutions, right? Because going down here, right? I talked about this part here, right? The taxi cab, right? Taxi cab distances, or Manhattan distance, right? This one here, right? So taxi cab distance, right, means it's like Manhattan and New York, right? That this road, this blue one, and a yellow road, same length. Now, same length, if you think about it in real life terms, is it the same cost really? Well, you have to take multiple left, right, left, right, left, right. Actually, not so great, actually, right? In the actual Manhattan, right? This is actually kind of bad road, I think, right? This is a drone road or bird road, right? Euclidean road, the green one, right? But if you're not allowed to do it, I would say the red one and the yellow one, right? They are probably going to be better ones, right? I wouldn't want to take money. I don't know. This is a very suspicious road, right? In fact, of course, in real life situations, you're probably not allowed to take too many left turns, right? Right. So. Yes, exactly. In fact, and this leads to actually things like interesting things. Actually, I think maybe we'll see some videos of the robot navigation ones, right? Sometimes there are competitions. They're still around, actually, right? I'll show you. Maybe I'll show the video. Yeah, let's go to the video. Robot navigation. Actually, I think it's part of a later lecture, but maybe I'll show you today. Robot navigation race, right? It's maybe not the wrong. Yeah, something like this, but this is like a maze. Yeah. So this one here. Let's look at this here, right? This advertisements are pretty good, right? So basic idea is this, right? You have the full knowledge, right? You know the map. They learn the map. But the solution is actually maybe not the shortest path. It is the one where you can race. Like maybe it's slightly longer, but you can actually like really accelerate, right? So you learn the accelerate. Let's see. This is a. Yeah. Let me see. Okay, let's look at this one. Wait, let's see.
The time mice get in the maze to 7 or 10 minutes, and mice are only allowed 5 runs from the start to the goal.
So if you spend a lot of time searching, that's a penalty.
Makes sense. So the strategy for most micromice is to spend their first run carefully learning the maze and looking for the best path to the goal, while not wasting too much time. Then they use their remaining tries to sprint down that path for the fastest runtime possible.
So yeah, but yeah, I think this is a video. I think there's sometimes, like I said, sometimes the shortest path is not the fastest path. That's one of the things, because you have these long stretches and you can accelerate. But yeah, the good video to watch actually. Maybe we'll add this. All right, so that's why I'm saying this Manhattan distance can be real life situations actually. So this might be slightly slower, right? Because it has extra turns, right? You know, cost something actually, right? So things to think about, right? So bidirectional search, right? So different heuristics. Another thing with heuristics, right? If your cheat code takes you forever to calculate, it's not really useful cheat code, right? I mean, it's kind of, then it's, you know, then you might as well use regular search, right? So if you're doing like 8 puzzle, right? The one here, right? This one here, right? Where is it? Oh, this one, yeah. What's a good rule to use actually? It's kind of hard, like how many pieces are off? Maybe that might be one rule, right? You know, that sort of like how do you evaluate if you're making progress? Maybe by how many pieces are in the right places, possibly. Now, where we are here, right? We're almost finished. We're getting close to finish for this day. Now, so functions. Also, another approach can be, you have a big problem, you can maybe generate some sub-problems and generate some solutions for these small sub-problems. That's a very valid approach. In fact, that's how, well, I would say, humans play chess somewhat like that, right? We learn patterns, right? What things work, right? And we can build from that. Many problems like can be sort of, okay, I know solution to this small maze, right? And I can use that to build something larger, right? So, good approach. Also, landmarks. Maybe you have some good checkpoints where you want to get between, right? So, so this is actually the cheat code that the online service use, right? They have some big, sort of like big, Google Maps supposedly use this approach too, right? Meaning they have some big like the major like destinations already pre-computed basically, right? So why is good? Because you only have to do it once, right? You have a caching, good approach. If you have memory, right? Trading space for memory, right? So this gets you speed, right? What's the trade-off, right? Exceptional speed, but you have to first set it up, right? If you do building some service, which you're going to do, you expect a lot of, usage out of this. It might be worse building it, right? So, again, probably, of course, like building a, self-driving taxis, right? For Riga, you'll probably want to build something, some sort of pre-computed some locations, basically, right? So how do we get better with this, right? So, okay, and we have, learning start better, So, we want to learn, so this leads to something more complex. Later on in the course we'll talk about this, how do we do learning, right? So, we capture some state, right? And see whether we can improve on this, right? So, we have some search space, right? You need to store, obviously you'll need to store some state, that's where you've been, right? And then see if you can actually make improvements on this, right? Build on this, right? So, of course, it means you need an algorithm to analyze what you did before, obviously, right? So, that's for next, not next lecture, but some lectures later on, right? So, experience, right? You store, so many problems, right? And you maybe, for example, you could build a pattern database, possibly, right? Right. So, again, oftentimes, we use some imperfect approximations, meaning, again, sort of like cheat code, but it maybe doesn't really work, right? But it kind of gives you sort of like a good estimate, right? So, when we deal, this goes towards the end of this course. We talk about reinforcement learning, right? Machine learning in general, but of course, reinforcement learning, this is basically what it does, basically, right? We have some data, right? And we are learning from that, basically, right? So, let's see what else, right? So, let's do a little summary on, so, if we have a single agent, right? A car or something, right? And deterministic, right? Simple rules. We do something. Fully observable. We know everything about what we are doing. Discrete, specific steps, right? There's no floats. It's just a distance, right? Unknown environment, right? Then we have these algorithms, right? Like Dijkstra, like A-star, right? They are very well. It's like like a basic starting point, basically, right? So you build a sort of like you have a graph, where you could possibly go, and you basically go through it, right? So again, this here, right? This is two-dimensional space, but we can of course imagine this could be, your movement doesn't have to be in 2 dimensions, could be multiple dimensions, obviously, right? Maybe you give me a problem and we'll see if this is not applicable, maybe. So give me some problem, right? Where this approach is not gonna work at all, right? Because anywhere you have to make a choice, this you can model this as a search strategy, right? So let's think of something which is let's see. Give me some problem. Anyone? Yeah, let's see. I don't know. Okay, yeah. Well, okay, but that's okay. That's easy, right? From to Rome, right? Yeah. I mean, then of course we have choices, right? So it's just a question of how you model this. Do you say, okay, do you assume that you can drive to Poland or can you drive through Russia, right? Yes. Yeah, so all roads lead to Rome, right? So exactly, right? So do you want? I mean, like I'm saying that's an easy problem because we already talked about this. I'm thinking of something completely different, something we didn't talk in this class. Can we model this as a search problem? Right. So, excuse me. Yes, solitaire. Yes. Oh, yeah, that's perfect. Okay, so let's load. I have my solitaire here, right? Yes. Okay. So we have this one is easy to, again, relatively speaking, right? Easy to define this. Wow, how? Come on. Okay, so classic solitaire, right? I don't want to sign in. Why do you need to sign in for solitaire, right?
You don't have to do anything, just like relax.
Yeah,
You're signing in.
yeah. I don't want to be on a cloud when I'm playing solitaire, right? So you have a starting space, that's your starting, right? And you know you have a very clearly defined goal, right? Where all the cards are there, right? And you have, at each moment, you have possible choices. You just basically draw a graph, right? You draw a graph of choices, right? You have possible states where you are, right? So state is the situational cards, like I put it, yeah. So that's a move, right? Yeah.
But
Yeah.
wasn't like the fact that we don't know what's like behind.
Oh yeah. That's the thing. We don't know what's behind these, right? But if we are trying to solve it, right? So we don't know what's happening, right? We don't have perfect information, right? If we knew what's behind them, right? Then we could solve it using these strategies, right? If we don't know, right? Well, why is it's doing this hint? I think it's getting annoyed. The cloud is getting annoyed that I'm not making the right move. Come on, okay. Right? So, like this, we can go here, right? Oh, yeah. So, notice it's kind of helping because, yeah. Okay. I think I may actually win this. No. Yeah. All right, let's win this, right? So, here we go, right? So notice how it does. If in the cases where there's no choice, they move it automatically, right? Good UI design, by the way, right?
You can move the jack to the queen.
Yeah. And I can be lazy, and I can do this. Yeah, and we're gonna do this, right? So K will go here, right?
Yeah.
And Jack, alright, let's see. This one goes here. Yeah, this has been. I'm getting. Oh, I don't like that one. Yeah. I guess one more. Let's see. 6, no, 5, I need 6, 7. Now we can do here. No. Are we kind of bad place? Anyone? 8? No. What is that? Yeah. Oh yeah. Sometimes, by the way, sometimes it might be useful to even put here actually, right? 9. All right. So 8. No?
Remove the last 8.
Can I do Control Z back? Oh. Oh yeah, it says in the cloud, right? Oh, I have a QR code, right? And I can go back to my game. Oh, but so that's good actually. It's a good thing I went back, right? So the point is, right, that we can model this, right? Right. So, I mean, my paint is going to be. So I have my starting game, right? I need something better to write. So my possible starting game where I have all the, here, right? I guess I'll do it one more time, right? Did anybody not, does it make sense that we can model the solitaire as a sort of like a search? We have a goal, we have a starting point, right? The only problem is that we don't have the full information. So it's not it's not what's missing. It's not fully. This part here is missing, right? It's not fully observable, right? So then we say, okay, it's not fully observable. We'll need something else. We need some heuristic, right? We can make some rules, right? But it's discrete. It's deterministic, right? Single agent, right? Just one player, right? So again, come on, reconnect. No. Any other problems? No? No, you don't have any problems. That's good. Right. That's good you don't have any problems. Okay, so what else did we touch on? So we look at different algorithms, right? So here's some also, if you are interested in some of these things, right? This goes way back, right? 15 puzzles from 19th century, right? Of course, Rubik's Cube, right? You can model Rubik's Cube. You have startings, you actually have multiple starting positions, right? But let's say you have a single, you have specific colors. Oh, wow. Oh, wow. I got, this is USB-C, right? Okay. You have multiple starting positions, but you have one specific, specific colors, right? You have a specific goal, right? All colors, right? And this was actually done by Google, right? They proved that you can do it in 20 moves, right? Google solving Rubik's Cube, right? Right. They proved it, I think, in about like, no, this is not this is just for you guys, for us humans. But for computers, they basically explore the full search space. They use some tricks, actually, like pre-computing some things as well, right? And they proved, I think, it's 20 moves, right? So any position, they went through all possible positions, starting positions. Any of them could be reached, I think, in 20 moves. Let me double check. So then I'll let you go once I finish Rubik's Cube. So big. Any speed cubers here? Anyone? Or maybe you know someone who is a speed cuber. Right.
There is one of our course mates from BBA.
Yeah, he's good.
Yeah, well, his best record was something like 12 seconds.
Wow, that's pretty good.
It was really nice.
Yeah. So, yeah, myself, I was like long time ago. I mean, it was, I thought a couple minutes was good. I thought, right? But of course, you've seen the speed cubers. What they do is they allow to check, right, and then they do it, right? Otherwise, it'd be no way, right? Right. So, right, practice. So what they do is, of course, they learn the sub steps, right? They know. It's like when we talked about the sub problems. Basically, they have certain positions where you know what to do, right? So, but what I want to tell you about is the proof, right? Limitations, patents, right? Mechanics, no. Okay, so that's positions, but algorithms. I'm going to show you what is the moves. Okay. 26 moves, 22. Yeah, Google proved God's number for Rubik's Cube is 20, right? Right. So.
They proved by just like faking.
Yeah. Yes, but they use some tricks, obviously, because it's like it's too big. The number is too big even for Google to calculate. Like they use some tricks, right? Yeah. God's number, right? Yeah. So they even proved that this is n squared divided by log n. That's kind of interesting. So n times n Rubik's Cube, like you have this big, 5 by 5 or 4 by 4, right? Even then you can prove this limit, right? That's very interesting, actually, right? Okay. So what are we going to do next on Thursday? Right? Searching, again, we'll look at something more complex, right? Complex environments, right? Right. So for you guys, thank you everyone. For you guys, you will need some extra, maybe we'll do some extra work on algorithms, maybe a little bit, right? I think, yeah.